Hello guys, hope all of you are doing great. This is part 9 of our 8086 programming tutorial. In this part of the video, we are going to learn a few theoretical concepts in 8086 programming. What I mean is this part of the video is not actually a programming part. Here we are not going to do specifically any programming. What we're going to do here is we're going to understand these few concepts, like what is memory segmentation, what is a physical address, what is segment registers, I mean what do actually they hold, and what are these offset registers. I mean what we mean by offset registers. All these concepts we are going to learn. Now see, these concepts are easy concepts actually, okay, and however this an understanding of these concepts are very much important to write 8086 programs, efficient 8086 programs, or say more as some you can write simple 8086 programs very easily without even worrying about these different concepts. But seriously, if you want to write some efficient and sort of useful 8086 programs, then certainly you need to have some understanding of these different concepts. And that's why I request you people to actually go through this video properly, and so that you become ready for all the programming tutorials which are coming after this part of the video. Don't worry, this will not take more than 10 minutes. These are very simple concepts, as I said earlier. It is just that you just have to see it once and you will immediately understand and remember those things. Okay, then let's begin. We know that in 8086 the address bus is of 20 bits and the data bus is of 16 bits. First, see what does that mean actually. When I say address bus is of 20 bits, it means the 8086 microprocessor is capable of pointing to or capable of accessing any one of these 2 to the power 20 bytes of memory location. It means you can think of the entire memory, the memory associated with this processor, you can think of it is divided into some bytes, say byte number 0, byte number 1, byte number 2, byte number 3, byte number 4, like that. This is the last byte number. So how many different bytes is possible if the address bus is 20 bits? It means byte 20 bits means this is 0 0 0 0 0 F. I mean F, I'm sorry, 0 0 0 0 H. H I'm writing to represent hexadecimal. So this is the 0th byte. So similarly, this will be the first byte, 0 0 0 0 1 in hexadecimal. So the last byte will be the last byte will be F F F F F H. See here, there are like 4 nibbles are there. So there are 5 nibbles there. So 5 into 4, 20 bits are there. So using 20 bits, the microprocessor is actually capable of pointing to or accessing any particular byte number from here, or any particular byte. It means it can go to any particular byte and it can read whatever the content of that byte. I mean, whatever the content of those, whatever the sequence of those 8 bits are, those 8 bits are, it can actually read those 8 bits. But the problem here is that the data bus, however, of this 8086 microprocessor is of 16 bits. It means from a program, if you want to refer to this memory location, you will not be able to refer to it, completely. In the sense that from a program, you can refer, or you can, see, since the data bus is 16 bits, so in a program you can mention only 16 bits your addresses. Even if you from a program, if you want to refer to a particular memory location, suppose from you are writing an 8086 program, and from that program you want to refer to say this particular memory location, say F A D 2 say 9, this particular memory location you want to refer to. You might be thinking, is it within the range? Yes, it is within the range. See here, all of them are hexadecimal digits. So these are 4 bits, 4 4 4 4 4, 4 into 5 is 16 bits, so it's a valid 4 into 5 is 20 bits, so this is a valid 20-bit address. Now, say for example, from your program, your data is there inside this particular memory location, and you want to access the data, which whatever it is there inside this memory location. So from your program, you directly cannot specify your memory location as this, because the maximum that you can specify is 16 bits, not like 20 bits. So that's a problem. But then also there should be some way to actually to point to this particular memory location, and there are ways actually, and how the problem is solved, like how the problem can be solved if somehow we can find the mechanism. Okay, we'll be specifying the addresses in 16 bits, but when the microprocessor actually try to access the actual memory location, it converts that 16-bit address to a 20-bit address, and that way the problem could be solved. Now the question is then how we can convert a 16-bit address to a 20-bit address. It could be done. You see here, uh, this entire memory, if you see this entire 1 byte of memory, 1 megabyte of memory, uh, you can think of you can think this entire memory is broken into some segments of 64 kilobytes of memory. Okay, so for example, this is your first segment, this is your second segment, this is your third one, like that. How many different segments of 64 kilobytes are possible in 1 MB 1 MB bytes? See here, we have totally 2 to the power 20 bits, so we need each segment to be 2 to the power 2 to the power 16 bits. So we have to multiply it by another 2 to 16 plus 4. So we need total 2 to the power 20. So we can write 2 to the power 20 as 2 to the power 4 into 2 to the power 16. It means we can write this thing as 16 into 64 kilobytes of block. Okay, there is the 16 different blocks could be there, and each block will be of 64 kilobyte. In 8086 program, any four of these blocks are used actually, and it requires four different blocks, and those blocks are called as, one block is called as your data segment. When I say data segment, it means it could be any one of these 64 kilobytes of block. Similarly, we have something called as code segment, we have something called as extra segment, and we have something called as stack segment. So these are the four segments there in 8086. Now, in 8086 memory. Okay. Now the thing is, yeah, see, this entire memory is like, to refer to any one of these byte number, actually we need 20 bits, right? But here the thing is, this entire memory is broken down into some 64 kilobytes of segments, and then what technique is used actually? See, each of these segments are actually, no matter whatever the segment you consider, each of these segments are now of 64 kilobyte. It means if you consider this segment as an independent memory unit, then to refer to any one of these bytes inside this memory, refer to any one of these bytes inside this memory, how many bits you need? You need only 16 bits, because there are like 2 to the 16 is 64 kilobytes. So if you have 16 bits, you can actually point to any one of these bytes inside this particular segment. So we can convert a 16-bit address to a 20-bit address if we know two things. One is in which segment we are in. Say for just for the sake of an example, let me say mark this thing as data segment, this thing as code segment, this thing as extra segment, and this thing as, say for example, stack segment. So first thing that we need to know is in which segment which segment we are referring to actually, in which segment our the actual memory is there. The first thing we need to know that thing. But once we know the segment, then immediately then the second thing that we need to know is inside this segment which byte number it is that we want to point to. Okay, so first thing is we need to know in which segment the actual memory is there, which we want our microprocessor to read. And then once we know the segment, also we want to know another thing. That thing is that inside that segment, what is the byte number inside that segment? That is, we consider inside that segment means considering the first byte inside that segment as the 0th byte and considering the last byte inside that segment as FFFF. Okay, byte number 0 to byte number 64 kilo. So inside that segment, which byte we are pointing to. So these are two things there. See here, first thing is that we need to specify which segment we are in. So that thing is actually, see, when we say which segment we are in, it could be anywhere actually, any of these segments it could be. So to refer to this particular segment, where the memory is actually, or from where we want to read the memory, in 8086 processor we use four designated in 8086 programming we use four designated registers, 16-bit registers that contains the starting address of these different segments. It means what? As the name itself indicates, so you can think we have, you know, right? There is this data segment register is there in 8086. There is this extra segment register is there. There is this stack segment register. There is this code segment register. Okay, let me write it vertically. Okay, data segment register is there. Extra segment register is there. Let me write it horizontally. I'm sorry. The stack segment register is there, and then code segment register is there. These are 16-bit registers, and what value we are going to store in this register, obviously they can occupy a 16-bit number. And what those 16-bit numbers will be? Those 16-bit numbers will be the starting address of the segment. Now you see here what I mean, why the starting address of a particular segment can be represented by by a 16-bit number. Why is it so? You see here, the starting address of these segments will be something where the last nibble will always be 0. Okay, so say here 0 0 0 0. Oh, sorry, yeah, that is 0 0 0 0. The 5 zeros are there. Okay, so it will be obviously 0 F F F F, the last address. And the first address of this byte will be, if it is just after this 64 kilobyte segment, then it will be 100008. Why it is 1008? See here, this F means all one. So if you add 1, then no, 1 plus 1 is 0, carry 1. So that way the 1 will be carried out to this last position, and all of them will become 0. So this will be the first byte of this particular segment. Similarly, for this segment, the last byte will be 1 F, 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 H. Okay, this is the last byte of this segment. So that way, if you consider the first byte of the first byte of any of these segments will have the last nibble as 0, and the first 16 bits or the first 4 nibble could be anything, any possible value. So for example, it could be like say I'm writing any possible hexadecimal number A, B, C, D. Just all of them are valid hexadecimal digits, so I can write A, B, C, D, 0. If it is A, B, C, D, 0, if the starting address is this, then we can write, okay, the last address will be, see here, it will be what? A, B, C, D, 0. And what will be the last address? If we want to know that, then we just have to add A, B, C, D, 0 plus FFFF. It is, see here, 0000 plus FFFF will give you 4 amps. 140 plus FFFF will give you 4 amps. Similarly, ABCD0 plus 4 amps will give you the last byte number in that particular segment. Okay, let me use this calculator and show you what ABCD0 plus FFFF. So I'll be using this calculator. See here. You can type in Google this hex calculator. It should show you this page. Any calculator, online calculator, or whatever the calculator that you have to do hexadecimal calculation, you can use it. I'm using this particular calculator, and let me type this to number ABCD0. Here it is ABCD0. It is not case sensitive. Plus I want to add here FFFF. So, or you can say I want to add 0FFFF. Okay, both are same. So it will give you BBCCF. That will be the last address of that particular segment. So this last address of that particular segment will be BBC. I forgot. BBCCF. BBCCF. Now see how we can convert a 16. So what we learned is that, okay, the starting address of the starting byte number for all these different segments should have this last nibble as 0. Okay, so if it is the case, then what we can consider is, since this last nibble is 0, then we can ignore it. We know that, okay, the last nibble will be this for the starting address of the first byte inside a particular segment. Only these 4 bits are only these 4 nibbles are enough, or only the 16 bits are enough. We can always consider, okay, the first byte will always have those last 4 bits as zeros. So that way what we can do is, in these different registers, we can store the first 16 bits of the first bytes in that particular segment. So in the data segment register, what value we are going to store? Suppose if it is the data segment register and if it is starting from A, B, C, D, 0, then what we are going to store here is A, B, C, D. Okay, the first 16 bits we'll be storing here. And why we can discard these last 4 bits, because we are assuming, okay, that will be anyhow 0. That is implicit. So for example, this is the extra segment. So in extra segment, what we are going to store in ES register, we are going to store the first 4 nibble, or the first 16 bits we are going to store. So for example, this is stack segment register, and let me just, for the sake of an example, I'm writing it that way. Say it is starting from B. See here, these segments, they cannot be overlapping segments, okay? But while giving the example, I might write some value here which are actually overlapping. But just for the sake of an example, assume that, okay, anyhow, whatever this number is, it should be bigger than B, B, C, C, F. Okay, let me write it carefully then. B, C, 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 F. So this is the starting address, okay? And starting with this is the, like, for stack segment, this is my starting address, or this is the byte number for the first byte. So in that case, the last byte will be certainly BCCF plus FFFF. That is inside this block. This is the 0th block. This is the F. This is the 0th byte. This is the FFFF byte. Okay. So that way, I guess if people understood what we should store here, we should store here BCCF. Similarly, for code segment, if it is this number here, if it is 1FFFF, then certainly what will be the next number here? The next number will be 20000, this particular. So code segment is starting from that address. So we have to store the first 16 bits, 2000. That's all in hexadecimal. So that way, what we know is these segment registers actually contains the starting address, or you can say it contains the first 16 bits of the starting byte of that particular segment. You got it? And also we can say that they contains the starting address of they contains the memory location of the starting byte inside that particular segment, because we can easily convert the 16-bit address to a valid 20-bit address just by appending a 0. What is the starting address of the first byte inside that particular segment? The actual memory location, it will be ABCD 0. It will be 00000. It will be BCCF 0. It will be 20000. All right. Then these are the segment registers. Then the question comes like, what is the offset register? Now see here, inside this segment, you see, now if you consider these segments, just by looking at the value of the segment register, we now know in which segment we are in. So once that question is solved, now the point is you can forget about all the things. Once that segment is fixed, okay, we are actually trying to access a memory location from this particular segment, then we can forget all the other things, and then we can concentrate on like how we can specify a particular location inside that particular segment. See, as I said earlier, only 16 bits are enough to point to any byte number inside a particular segment. Right? So it means we just need a 16-bit number actually, and those numbers, there are some designated registers where we can store those 16-bit numbers to do the calculations. Okay, so for DS segment, the designated registers are you can use either BX register, you can use BP register, you can use source index register, or destination index register. I mean, see, all these registers are 16 bits register, right? So these registers you can use to hold the 16-bit byte number inside the data segment register, and that that 16-bit number inside a particular segment register is called as the offset. See here, inside stack segment at the offset 0 is actually the 0th byte or the first byte, you can say. The last offset is FFFF. Say from say, just for the sake of an example, suppose you are in DS segment, you want to access byte number 23. So that particular location is what? First, you have to go to DS segment. You need to know what is the first address of the first byte inside this DS segment. It is ABCD. So you know what is the first address, then ABCD 0. So ABCD 0 is you directly reach here. And from here, you have to go 23 down. So 0, this is the 0th one, first, second, third, fourth, like that. At some point of time, you'll go to the 20, no, you will reach this 23rd byte there. And that is actually the that is the actual memory that your program actually or your microprocessor should read. Okay, so that way the, these 16-bit byte number inside a particular segment is called as the offset. And for different segment registers, I mean for different segments, different you have to use different offset registers in a program. Okay, you will come to know maybe in the next video, like, okay, you will come to know this in while I'll be discussing about addressing more. Okay, but the thing is, for the time being, what you need to remember is inside for a particular segment, these offset registers, I mean only these registers, these are the designated registers that can be used or that can be used to store the offset. Say for example, if you are using data, if you are trying to access the memory location, you are trying to access a memory location which is there in data segment, then you can use any one of these four registers to hold the offset value. You cannot use actually AX to hold the offset value if you want to access a memory from data segment. You will come to know that, but anyhow, for the time being, this much only. Then for extra segment, what is the offset register, or what register you can use as offset register, or what register you can use to store the 16-bit offset? There is only one actually, that is destination index register. For stack pointer, you can use either BP register, the base pointer register, or stack pointer register. For code segment, you know, right? That is the instruction pointer. So for code segment, the instruction pointer is used to point to the offset, or it is used to hold the offset. And this stack segment I have not discussed much till now, but in my coming videos certainly I'll be addressing them. Extra segment I have not discussed. I'll be discussing them in my coming videos. And data segment we have used, but not exactly in terms of these different segment registers. I mean different offset registers. You will come to know about all these maybe in the next video. Don't worry. But for the time being, what we have to know, or what in this video I tried to convey you, is that the entire memory of the first point is that in 8086 the address bus is of 20 bits. So that way the 8086 processor is capable of capable of accessing any byte within the range of 0 to FFFF within these 1 megabyte different possible values. But the thing is, again, the data bus is of 16 bits. It means from a program, if you want to access a particular location, if you want to specify like a particular location there, then you are actually allowed to specify only 16 bits, not the complete 20 bits. So for that reason, what happens is the addressing of 8086 is sort of the addresses of 8086, the actual physical address of in 8086 programming is actually has to be calculated. You cannot specify directly. Okay, and for that calculation, we use some techniques. The first technique is that the entire memory will be broken down into some 64 kilobytes of segments. So that way, this 1 MB entire big memory can be broken down into 1664 kilobytes of segments. And out of these 16 segments, we need only 4 segments actually. And one segment will be used as data segment, one segment will be used as code segment, one will be extra, one will be stack segment. Okay, and out of which this code segment, as you know, it actually contains the code of the actual code of the program. Okay, obviously in binary, like after converting the assembly code to binary code, whatever it is, that actually is stored in this code segment registers. And the rest of the register, or the rest of the segments, you can you can use to store program data. I mean, whatever the data on which your program is operating on. But the point is that all these different segments are of 64 kilobytes now. Now, if they are of 64 kilobytes, then one 16-bit number will be enough to point to any particular memory location inside that particular segment. So to access any particular memory location, in the available 1 MB memory, what we have to do is, from a 8086 program, we have to specify two things. One is in which segment that particular memory location is there, and inside that segment, what is the actual byte number of that memory location. So, so those two things are specified by using two different sets of registers. One sets of registers are used to hold the starting address of the segments. When I say starting address, obviously any address of these memory locations will be of 20 bits. But the thing is, we choose the starting address in such a way that, okay, the first nibble is always 0. So that way, what we can do is we can use the first 16 bits as the starting address of, like, if we only know the first 16 bits, then immediately we know which byte we are actually talking about. So that way, the first 16 bits of the starting address of a particular segment is stored in these corresponding segment registers. So for example, in this picture, extra segment is starting from 00000, so we'll be storing here in ES 0000, the first 4 nibbles. Similarly, code segment is starting from 4 zeros, so it will be storing 2 3 zeros. Similarly, data segment is ABCD0, so we'll be storing ABCD as the starting address of the data segment. Stack segment, same way, it is starting from DCCF0, so we'll be storing DCCF. One thing is that the starting address always should have this last nibble as 0. Okay, obviously, I mean, you should realize that point. And then once we have this starting address in some registers, also we have some designated registers to specify the offset. For different segments, we have different designated registers. Say for example, in data segment, if you want to specify the offset, you can use any one of these 4 registers. In extra segment, if you want to specify the offset, then you can use this register. That is, you can store the offset value in this DI register, or destination index register. Or in stack segment, if you want to specify the offset value, you can store the offset in any one of these 16-bit register. Similarly, in code segment, if you want to specify, I mean, in code segment is sort of, you do not do it programmatically, more or less. It is in instruction point. Okay, then now suppose, okay, if you have understood this point, then you should be able to answer this question. So for example, if you know what is the value of the data segment register, if you know what is the value of, say, BX register, can you compute the actual physical location, actual physical PHYSICL, physical address? When I say actual physical address, means the 20-bit address in the available memory, in this available 1 MB memory. We know two things, data segment, we know what is the BX, we know. We have to compute the actual physical address. See, data segment will be of 16 bits. It could be anything, say A, B, 0, 2, say. And BX is also of 16 bits, so that way BX also could be anything, any valid 16-bit number. Say it is 2092. So what will be the actual physical address? It is not simply DS plus BX, right? Obviously, people know that, yes. So what it will be? So we know that this data segment actually contains the starting address of the segment, or what it contains is, it contains the address of the first byte inside that particular segment. In the sense that, in some way, actually, not exactly. And what in some way means, this, the first byte, if we know the data segment is AB02, then what we know immediately, we know that the address of the first byte will be AB020H, right? If the content of the data segment register is AB02, then immediately we know that the starting address of the first byte in the data segment register will be, the actual physical address will be AB020H. What exactly, how we can convert AB02 to AB0208? Yeah, see, these are 4 bits. Okay, these are nibbles. These are 4 bits. These are 4 bits. These are 4 bits, 4 bits, 4 bits, and 4 bits. Initially, you had 16. Now you're converting it to 20. And how we do that? Yes, we can actually do it. We can do it simply by left shifting this DS register by 4 bits. So that way, if we left shift any one of these segment registers by 4 bits, then we immediately know what is the starting address. So what is the starting address of the, or what is the address of the first byte which is there in the stack segment register? If the the stack segment has this value BCCF, yes, we just have to shift it towards left by 4 bits. It will be BCCF and 0, isn't it? So once we have these starting address, that is once we know this left shifting by 4 bits is same as, if you know, multiplied by 16, actually 16 in decimal, or it is same as actually DS multiplied by 10 in hexadecimal. All these are same things, and all these will basically put whatever the content of this DS register, whatever it is, after that it will put a 0. It will bring a 0, extra 0, and it will convert it to a from a 16 to 20 bit address. Now that way we know the starting address. Now once we know the starting address, we know what is this offset is pointing to. I mean, what is the use of this offset? These offset actually specify, okay, starting from this, I mean from this starting inside that particular segment, how many bytes we have to go. This 2092 means it is the 2092 bytes inside that data segment register. So it means what? If the data segment register is containing AB02, then the BX is 2092, then the actual address will be computed. First, we have to shift it towards left by 4 bits to convert these AB02 to AB02 will become first AB020, and with that we have to add the offset address, that is 2092. So we'll be adding 2092. So whatever it is, 9 plus 2 is 11. 11 is what? B, and then 0, B plus 2, C and D, and then this. So this will be the actual physical address if data segment is AB02 and BX is 2092. So that's how it is calculated. How it is calculated? Simple. You just have to left shift it by 4. Technically, if you want to specify, or otherwise, only to know, you just have to append a 0 at the end, and then you have to add whatever it is the offset value, 16-bit offset value to it, and you will immediately know what will be the the address, the actual physical address. That's how it is calculated. I guess you people got the idea, okay? But here, these are some things that you have to remember. Like, what are the registers you can use actually? See, there are many different registers, like 16 registers that you cannot use all of them as to hold the offset. If you are trying to access a memory location within data segment register, you can use any one of them. But if you are trying to access a memory location within extra segment, then you are allowed to use only one register to hold the offset. Similarly, for stack segment, you can use these 2 registers. For code segment, you can use these IP registers. Okay, guys, then that much only. I hope people understood. If you have any doubts or queries, you people can let me know it in the comment section. See you guys in the next video. Till then, have a nice day.